Okay, this is a pre-calc video over Unit 2, Section 4, and this is graphs of polynomial functions. So what we want to do today, our objectives, we want to identify the key features of a polynomial function from a given graph. We want to describe the key features of a polynomial function, okay? So, when you have a polynomial, that's a function where you've got you can tell a lot of information based off of the graph, and you can tell a lot of information if you're given the function itself. You can kind of tell a lot about what happens on the graph. So, but we have all these different characteristics, okay? So a polynomial has a degree, has the sign of leading coefficient, has a domain and range, has end behavior, has turning points, has local maximum, local minimum, and it has x-intercepts, okay? We need to be able to figure out all of these things given an equation or given a graph. So let's kind of talk about some terms that we have here, and I'm going to try and put this in the simplest terms. And so what we have here, we have all these different things, okay? We have a polynomial function, and what we see here is we see a polynomial function whose we've got all these different terms, some coefficient, some variable raised to a power. And then every subsequent term, the power, or the exponent, goes down, and it decreases until you have just x to the first, and then, you don't have any variables. So an example of this, all right, would just be something like, and I'm going to come in here, I'm going to zoom way in. So an example we would see here would be like, say, f of x is equal to 3x to the fourth plus 2x cubed plus 5x squared plus, 4x plus 7, okay? Now, what I want you to notice here is that, I have values in front of my variable. These are the coefficients, okay? 3 is my leading coefficient. The one thing I do want you to notice is that my exponents go in descending order, okay? So I've got 4, 3, 2, 1, and then 0, okay? So this is in standard form. Usually that's how you'd want to make it, so that your exponents are ordered from left to right, that they go in descending order like that, okay? Okay, the next one is the degree. Okay, the degree is an important word, okay? And this is the largest exponent of a function, or of a polynomial. Polynomial, okay? So the example I have here, let's just kind of continue to use this function that I've created here. My largest exponent here is 4, okay? So from above, this equation here, the degree is equal to 4, okay? And because that's our largest exponent, is 4, okay? The next one is standard form. Now, standard form means that, and I'm going to come in here, that's a polynomial whose terms with exponents go in descending order. Exponents go from big to small. Okay. And I'm just going to say here that this is in standard form. Okay, and remember that's when the exponents go from big to small. Okay. The last one is the leading coefficient, and that is the number in front of the first term when a polynomial is in standard form. a polynomial is in standard form. Okay, so if we were to talk about this, I would say that here's my first term with my in standard form with my largest degree. This value of 3, all right, 3 is our leading coefficient. And I use COEFF to stand for coefficient. Okay, remember coefficient is the number in front of the variable, but the leading one is important. That gives us a lot of information. So we do need to understand, what a polynomial function is. We really need to understand the word degree, and we really need to understand the word leading coefficient and know what those mean. Okay, it is imperative for our understanding. Okay, now let's go over here and let's say, all right, which of these polynomial functions are written in standard form? Okay, and I want you to select all that apply. I'm going to give you a minute to do that real quick. Okay, you guys should have put this function, this polynomial, and then this polynomial. Okay, the reason why is because the exponents go from large to small. Okay, here you got an exponent of 5, exponent of 1, and then exponent of 3. Okay, so that order isn't right. Okay, here they have 3 and then 2. So that works. Okay, so the leading coefficient of this one, so leading coefficient is equal to -3. Okay, here on this one, the leading coefficient, lead coef, is equal to +1. All right, so either one of those works. Okay? Okay, let's go ahead and let's get our calculator, or let's open up our Desmos calculators, and let's actually graph these, and let's see if we notice any similarities or differences. Let's go ahead and just graph all those in our calculator. I will do the same, and then we'll take a look at them. Let me say that. Okay, so we've graphed these, and what we noticed is that if you have an odd degree, so we notice that an odd degree, okay, odd degree, we know that the functions are strictly increasing. So here's, y equals x squared. The green graph was x cubed, okay, and the orange graph was x to the 5th, okay, and they all kind of share this thing where they just keep increasing. So they are strictly increasing. So odd degree means you are strictly increasing. Okay, if you have an even degree, that meant that you went from decreasing to increasing. You kind of had a parabola shape. You always had a minimum value. So even degree means you go from decreasing to increase. Okay, and that's what you've got. Okay, so odd-numbered functions kind of behave the same way. Okay, even-numbered functions behave the same way. And so you can answer this question over here. It says, without graphing, which of the following do you think would best describe the graph of the function y equals x to the 8? So when you have x to the 8, the degree is 8. The degree is 8, which is an even number, okay? And so it would behave most like another function that has an even degree, okay, like x squared. Okay, it wouldn't behave like y equals x or y equals x cubed. It'd behave more like x squared because the degree here, the degree is 2, which is even. Okay, and that's the key, is that they're both even. The degrees are even. They kind of behave the same way. Okay, they're not going to be the same, but the behavior is the same. Okay, all right. So now, all right. Let's kind of take a look at these problems down here where it shows, what's happening. And I want you to see that, in this you've got y equals x squared, y equals x cubed, y equals x to the 4th. Okay. What I want you to know, all right. First things first. Let's take a look. Let's take our degree our degree, our exponent is 1, okay? So our graph is strictly increasing, okay? And then our leading coefficient is positive, okay? So our end behavior means that we're going to go down to the left, down left, and then up right, okay? And so we kind of learned that last unit, but we're kind of putting this all together now to do the same thing, okay? Here, okay, again, our degree is 2, which is even, okay? Our leading coefficient, our lead coefficient is positive 1, okay? So that means that our end behavior is going to be up to the left, okay? And then it's going to be up to the right as well. Same thing over on this next one, okay? Our degree is odd. Our degree is 3, which is odd, okay? And then our leading coefficient is positive. So lead coefficient is positive. So that if we look at our end behavior there, okay, since our degree is odd, they're not going to have the same end behavior on both sides, okay? They're going to be opposites. But because our leading coefficient is positive, we're going to go down to the left, okay, down left, and then up to the right, okay? And then similarly with y equals x to the 4th, okay, our degree is 4, okay, which is an even number. And our leading coefficient is positive, okay? And then that means that we're going to go up to the left, and then up to the right. All right? So notice that, you know, if our degree was even, okay, then our end behavior goes the same direction on both, okay? So degree 2 and degree 4, those are kind of like the same problem, okay? We're kind of answering the same question. If our degree is 1, okay, then they go in opposite directions, all right? So, you know, the thing that's similar about all 4 of these graphs is that our leading coefficient here is positive, okay? But what happens when our leading coefficient is negative, okay? So here, what you see, okay, you've got degree 1, which is odd, and then the leading coefficient is negative. So that means that we're going to go up to the left and then down to the right. Okay? And so what you can tell here is that, you know, these graphs of y equals x and y equals negative x are very similar. Okay? However, the only difference is the end behavior, and that's because of our leading coefficient has changed. All right, so same thing down here. All right, our degree is 2, which is even. Okay, our leading coefficient is negative. Okay, so then we go down to the left, down left, up right. Okay, similarly over here, leading coefficient, or I'm sorry, our degree is 3, which is odd, and our leading coefficient is negative. So that means we're going to go up to the left and then down to the right. All right, last one, degree is even, degree is 4. Okay, our leading coefficient is negative, and that means we're going to go down to the left, up to the right. So our, you know, what we want you guys to be able to do is be able to look at a function, okay, identify what the largest exponent is, and then, you know, determine, okay, what kind of exponent do I have? What's my leading coefficient doing? And then, boom, I know what the graph is going to look like end behavior-wise, okay? That's kind of it. So then, okay, so then here, let's just take a look. So you know, if you're given a graph, okay, it goes, you know, up to the left, down to the right. So what do we know about that degree? Is it going to be odd or even? The degree. Well, yeah, look, you know, in the thing of it is the end behavior, as x gets infinitely small, what are the y values doing? Are the y values going up? Okay. Over here to the right, as x gets infinitely large, the y values are going down. So if the end behavior is going in opposite directions, you know that the degree is odd. Okay, of odd degree. And then we know that the leading coefficient is actually negative. Okay? And I'm just kind of looking, you know, the graph kind of looks like this over here. All right? So my degree was odd because my end behavior went up to the left and then down to the right. All right? And then my leading coefficient was negative, which gave us that. Okay? So what I want you guys to do, I'm going to give you a couple minutes to do this next one. All right? And you're just looking at end behavior here. You're allowing end behavior to kind of tell you what's going on with that function. I'm going to give you a minute to do that. Okay, so for this one, what I see is that my end behavior, and let's write that down. Our end behavior means we're going down to the left and down to the right. All right? So when I take a look at that, oh gosh, what am I doing? Because these are all screwed up over here. This should be down to the right. Sorry. Ugh. And this should be down to the right. My bad. Maybe that's why you're confused. Okay, so change those up. Okay, they all look good. All right, so then what we want to do is we want to take a look and say, all right, since they're going in the same direction, okay, that means that it's got a graph that looks kind of like this and kind of like this. All right, so what I'm going to do, I know that the degree of this is even. But since they're both going down, okay, going down and down like these are, then I know that my leading coefficient has to be negative. All right, so my leading coefficient is negative. Sorry about the confusion. All right. But that's what we want to do. We want to be able to just look at a graph and say, okay, what's my end behavior? If my end behavior is this, then I know that my leading coefficient and my degree are this. Okay, you got to be able to look at a graph and know what those are going to look like. Okay, and also, given an equation, know what the graph's going to look like. So you have to go from the graph to the equation and from the equation to the graph. All right, so that is important that we do that. Okay. All right, on this one, it's asking what is the domain? Okay, and the domain, remember, what's domain? What else can we think of when we hear the word domain? What do we think of?
Y.
Not y. X values. Domain is the same thing as saying x values. Okay. And so it says, what is the domain? Another question would be, where are the x values? Okay, so I'm going to write that. I'm going to say, where are the x values? Okay, and the unique thing about any polynomial is that the domain, any polynomial, the domain is going to be from negative infinity to positive infinity. Okay, so the domain is going to be from negative infinity to positive infinity. Another way of saying that is all real numbers. Okay, but this is the case for any polynomial. Any polynomial is going to have that, where the domain is the set of all real numbers from negative infinity to positive infinity. Okay, and the question is, what is the range? And what does range mean? If domain is x values, what the range is the what?
The y values.
Yeah, it's the y values. okay? And so it says, where are the y values? Okay? Now this function here, okay, and here's what I know. Okay, the end behavior, as I look at this graph, as x gets infinitely small, the y values go up. Okay, so we go up to the left, so up left, and we go down to the right. So as the x values get big, the y values get small. So up to the left, and we're going to go down to the right. All right. So what we know is that the y values, you know, we have from negative infinity, from bottom to top, we go from negative infinity to positive infinity. So we get something really similar here, negative infinity to positive infinity, and that's all real numbers as well. All real numbers, okay? And this, you know, when we had any polynomial, we knew that you know, our domain goes from negative infinity to positive infinity. But what I know from this is that my degree of this function has to be odd because the end behavior is going in opposite directions, okay? So because my degree is odd, that's going to be the case. Now this is going to be the case. It's going to be all real numbers always for odd degree. Okay, that's important that we know that. Okay, if it's an even degree, then our domain is actually going to be restricted. Okay, and let's come over here, and we're going to write that this is a continuous function. And we learned about this in calculus too. Okay, because there are no breaks in the graph. Basically, continuous function, that is a vocab word. We need to be able to understand what that is. A continuous function means that you can draw the graph without lifting your pencil. Draw the graph without lifting your pencil. Okay? All right, here's the next page. Let's go ahead and take a look at this graph. And it says, which is the possible leading term for the graph shown? Okay, so what you have here is you have this graph here, all right, and we want the possible leading term. Okay, now let's take a look at the end behavior. Let's just write out here. The end behavior means we go down to the left and up to the right. And so what if the end behavior is opposite, then what do we know has to be the degree of our function? Then our degree must be odd. Okay? And since we're going down to the left and up to the right, okay, that means our leading coefficient has to be positive. Okay? And so if we want a leading coefficient that's positive and an odd degree, then the only choice that we could choose is something like this. Okay, that's a possible leading coefficient. Doesn't mean that it is, but it's the only one up there that works. Okay, all right, and so we know as x approaches positive infinity, okay, then the y values approach also positive infinity. Okay, as x approaches negative infinity, then the y values approach negative infinity. Okay. All right, and so what we have here is we have these things called turning points, okay? And a point where a function changes from increasing to decreasing or from decreasing to increasing. We've talked about that. And this is where you get maximums and minimums. So you get max and mins, okay? And so we know that, that it says that a local maximum is where the greatest value of a function over a specified open interval. Okay, and then a local minimum is the least value of a function over the specified open interval. So let's rewrite that. A local maximum, that's the largest y value, okay, over an interval. A local minimum is your smallest y value. Okay. And we also have a maximum when we change from, when our graph goes from increasing to decreasing, okay? and I'm going to write increasing to decreasing. Okay, that gives us a maximum value. A local minimum is where you go from decreasing to increasing. Okay, and you get a minimum value there. So you go from decrease to increase. All right, and as a result, what we know is that the maximum number of turning points is one less than the degree. So what we said here is we said that this degree here was odd, okay? And if we take a look at this 2x cubed, notice that we go from increasing to decreasing. So, and I'm going to write that. We went from increasing to decreasing, okay? And then all of a sudden here, our graph actually does increase a little bit. And then we continue to decrease again, and then we change back to increasing. Okay, now I want you to take a look at this in that our graph changes from increasing to decreasing, decreasing to increasing, increasing to decreasing, and then decreasing to increasing. Okay, so we got quite a few. So here you have a maximum. Okay, because you changed from increasing to decreasing. Okay, here, you have a minimum because you changed from decreasing to increasing. Here you go from increasing to decreasing, so this is a maximum here. And then down over here, okay, you change from decreasing to increasing, so you have a minimum. Okay. So you can kind of just look at the graphs and it's like, okay, where do you have a high point? Where do you have a low point? Okay, if you were skiing this, you get to the top of a mountain, okay? And then you slide down and then you go back up again and then you go back down and then you go back up. Are you going uphill or are you going downhill from left to right? And that's how you can tell if you're increasing or decreasing or not. Okay, kind of hard. All right, let's take a look. Okay, so it says, what is the local max? Okay, so how many turning points does this graph have? So this graph right here has 1 turning point, 2 turning points. Okay, so you have 2 turning points. All right, so that means that our degree is going to be 1 larger than our turning point. Our degree is going to be 3. Okay, and it wants to know what is our local maximum. Okay, so our local max, here's what we've got. We go from decreasing to increasing and then decreasing again. Okay, here's our minimum. Okay, and the y value of that minimum is a value of -2. So the local minimum is -2. All right. Here's our maximum y value, maximum, when it changes. And that y value is a y value of +2. Okay? All right, so now let's take a look here. Let's see, this is the same graph. Okay, we were decreasing here, we were decreasing here, and then we were increasing from here to here. All right, so it says that when x is less than -1, so when x is less than -1, the function was decreasing. Okay, it was going down. All right. Now from -1 to +1, and these are the x values, okay, from -1 to +1, the function was increasing. Okay, over that interval. Okay, and then if we say that x is greater than +1, then we know that the function was decreasing. I don't think that's on there. Is that on your paper? Or is it just those two? Just two? Okay. All right, and then it says, all right, select all possible degrees of this function. So you have how many turning points? You've got a minimum and a maximum. Okay, you've got 2 turning points, so the possible degree would be 3. Okay, you could potentially do 5. That's a maybe, but I would just choose 3. That's the one that you know for sure. Okay, but it could have an odd degree because of your end behavior. Okay, and we'll kind of talk about how that would work and how it wouldn't work. Do you guys have something on the bottom of your page here? Another problem?
It's like a link.
It's a what?
It looks like a link.
A link? Link up the chains, bro.
The other ones in this.
Okay, let's take a look at these last few problems, and let's zoom in on this first one up here. It says, given the values in the table on the left from a continuous function, which intervals must contain an x-intercept? Okay, now first of all, an x-intercept occurs when y equals 0. Okay, when y equals 0, you have an x-intercept. So here's what I know, okay? That, you know, and it's when the y values change from negative to positive or positive to negative, okay, is what I'm looking at. So here, all right here is where I notice that the y values change from positive to negative. So what we know is that in order for, you know, at some point in between negative 3.2 and 2.4, negative 2.4, you had to have a y value of 0. Let's just kind of sketch a graph of this too. All right. So here's negative 2.4. Here's negative 3.6. Okay. Or I'm sorry, 3.2. All right. And what I know is that at negative 3.2, I had a y value of negative 1.19. Okay, negative 1.19. And then at negative 2.4, I had a y value of 4.62. All right, so I had this. So in order for me to have a continuous function, okay, I had to go through the x-axis at some point. Okay? Looking at a table of values can kind of show you, but this graph kind of helps solidify that. And that's what we're looking for. Okay, when that graph, if I know that a y value goes from negative to positive or from positive to negative, at some point in between these two x values, it had to go through 0. It had to go through the x-axis. Okay, so where else does that occur? Okay, so that occurs between, you know, negative 3.2 and 2.4, okay, and that's this value right here. And then, okay, we have a possible, all right, you could have one here as well. So between negative 1.6 and negative 0.8, although that's not one of our options here, okay. The other one would be here, between negative 4.7 and positive 7.26, okay, and that occurs between 1.6 and 2.4. So both of those would work. Okay, so you're looking for when does y equal 0, and if you're looking at a table of values, you know, where does that line, you know, where do your y values go from positive to negative or negative to positive? Okay. Okay, let's take a look at the next one. Okay, given the values in the table on the right from a continuous function, y has at least how many zeros? Okay. So again, where does it go from positive to negative or negative to positive? And that occurs here. So that's 1. It occurs here. That's 2. And then it occurs here. So you would have a total number of 3. Okay. So, and over here, and let's just write over here that this is where the signs change. Okay, that's all I'm looking for, the sign change on those tables. All right, and same thing over here. Okay, this is where all 3 of these, the sign changes. Okay, so it must have a y value of 0. Okay? All right. All right, let's take a look at this last one, and then we'll stop the video. And on this, it says, you've got this graph over here. You've got this function. And what you notice, first of all, this is called deer population. All right, so we're analyzing how many deer, the number of deer, over a certain amount of time. Okay, and when I look at that graph, I'm looking at these axes. I'm looking at the labels to help me understand what's going on here. Okay, so as the time goes on, the amount of deer fluctuates. Okay, so it says, what is the meaning of the domain and range? So remember, domain is x values. So let's come in here. Okay, domain, that means x values. Okay, and so what do the x values represent in this case? What's the label along that x-axis? What does it say on that graph? Look at that graph. X is time. Okay, you have to understand, first of all, domain, x values. Automatically, every time you hear that word domain, you know that those are x values. Okay? Then you just look at the thing and it says time in years. Time, and that's in years. Okay? All right, the other one, range. Okay, if domain is x values, then range means y values. Okay? And what's the label on that y value? On that y-axis? It's the number of deer. Okay, so this is a function of time to deer. So for whatever year it is, okay, how many deer are there? All right? And then it says, what does the x-intercepts represent? All right, here's an x-intercept, and that's when the population of deer is 0. Okay, that means you have no deer. 0 deer.
Is it possible to have negative time? Or is it just a continuation?
Yeah, it's just a continuation. What they've done is they've said, okay, the model, the model or the data fits this equation, fits this graph. So you could write a graph. If you're talking about this, I mean, you could be talking about, like, say that this is the year 2000. And before that, what was happening. But you can't also have negative deer, though, too. So that's a good observation. Yeah, you either have 0 deer or you have deer. You don't have negative deer. You're not owed deer. It's not like money where you can have negative money. So yeah, good observation. But when you do have a population of 0, that's it. You have no deer. Okay, 0 deer. You could also say a population of 0. And what happens when you have a population of 0? What do we call that? Begins with an E. Extinction. Yeah. I mean, and it raises a decent question of the whole concept of, like, Jurassic Park. Could you recreate dinosaurs if they're extinct? That's a whole other question. One time kids came up to me at my old school and they go, hey, Mr. Police, do you have any, like, movie ideas that you're just, like, hanging on to? And I was like, yeah. I have this idea where we recreate dinosaurs and then we put them in a park. And then, like, all of a sudden, like, the power goes out and the dinosaurs escape. And so we're trying to get the people out before the dinosaurs eat them. And the kids were like, sounds a lot like Jurassic Park. Okay. Okay, so what's happening at the turning points? Let's take a look. Okay, so here, and let's just look at this graph. And you can, you think about this and you go, okay, as time increases, from here to here, the population of deer increases. It's going up. Okay, here, something happens and the population goes down. Probably humans with their guns, killing the deer for the antlers and for the venison, which is delicious. Okay, but then all of a sudden, the graph goes back up again. The population goes way up. So here, you had a maximum number of deer. Okay, this is a maximum, but you had a maximum number of deer. Here, you had a minimum number of deer. All right? And so, what's happening at the turning points? the population of the deer is changing, okay? At the max, and that's kind of a hard question to ask or answer. It's like, what's happening at the turning points? Well, you either had a maximum or minimum number of deer. Here, the population was increasing. You had a maximum, and then they started to die off. And then something happened down here after like 60 years, and then all of a sudden the population skyrockets. And there's things that affect that. I mean, that's why they have these models and they have these predictions, is because, there are reasons why this is happening. Typically, the population was increasing. They didn't have any natural predators. Humans weren't killing them. Okay, and so they flourished. And then maybe all of a sudden, and the same kind of thing happened actually in Yellowstone, because they reintroduced the wolf into Yellowstone. And what happened is that when there were no wolves, the deers ran rampant and the population increased. And then their food source, like they were just eating all the grass, and so all of a sudden that affected like the river change. And then they were like, all right, let's bring the wolves back in. And then all of a sudden the wolves started eating the deer. The river started to go back to normal. And then maybe something happened to the wolves, and then all of a sudden the population of deer goes way up. So, yeah.
Will it follow that pattern? Like, what will happen? Or does that depend on the
This is, if this is the case of the deer population, then the deer population is just going to go up. It's going to infinity. But eventually it'll have to die off. So it's not a really good model, but it does kind of tell us something. Okay, I'm done.